All right. Hello, everybody, and thank you for your patience. Just a quick introduction. Before I introduce today's speaker, just a word. Our next and final speaker for this semester will be on December 6th, and it'll be Professor Stephen Ralph from the School of Electrical and Computer Engineering, also director of the Georgia Electronic Design Center. So it's a pleasure to have with us today Akanksha Menon. Professor Menon got her bachelor's degree at Texas A&M University in Qatar in mechanical engineering, and then came to Georgia Tech to get her master's and PhD, and then went off to do a postdoc at Lawrence Berkeley Laboratory before coming back to Georgia Tech in 2021, where she's currently an assistant professor in the School of Mechanical Engineering. She's received a number of awards and recognitions, most recently from the Falling Walls Breakthrough of the Year Emerging Talent recognition, as well as recognition from the Department of Energy Women at Energy program. And I'll turn it over to Akanksha.
Thank you, David. All right, good afternoon, everyone. Sincere apologies for being late. I last minute agreed to guest lecture for someone and had to make my way across campus, but thank you all for being here, and I'll try to still get this done within the 40 to 45 minutes that we have. So like David said, I'm a relatively new assistant professor here, and my group is called the Water Energy Research Lab, and we mainly focus on using functional materials and thermal science in order to develop better desalination as well as energy harvesting technologies. And so the reason why we're interested in this work is if you look very high level, even for the next few decades, we're still going to be heavily reliant on our fossil fuels for electricity production. And so this is really a big motivator to look at ways in which we can continue to decarbonize energy. And then if we look on the water side, by the end of this decade, so by 2030, we see that about half of the global population is going to be experiencing severe water stress, meaning that we are depleting our naturally occurring freshwater resources, and we really need to think of ways in order to increase our water resources. So this is a Sankey diagram that kind of shows you how water and energy are so closely related and linked. So here we have all the different, I'm gonna walk over here, with our different energy sources, most of which is used for transportation, residential or commercial buildings, as well as for industrial applications and electricity generation. And then down here we have all our water sources. So this is our fresh water that's available. And we see that a large amount of our water is used for power generation, so for cooling power plants. And then the rest of it, or a large amount, is used for agriculture. And what I want to draw your attention to, if we follow these lines after it's utilized in these different sectors, what you notice is about 60% of the energy that we started with is just dissipated as waste heat. And about 70% of the water that we started with is just discharged as contaminated water. And so we have this very linear model. And what we're interested in is thinking about ways in which we can recover and reuse both energy and water, and also thinking about ways in which we can decarbonize these energy systems. And so one thing you may have come across a lot is this water-energy nexus. And all that's telling us is that water and energy are very closely coupled. So for any energy production process, whether it's extracting or refining your fuel, producing power, or cooling your power plant, you require a lot of water for those processes. And on the reverse side, if we look at extracting clean water, energy is required for that extraction, for purification, for distribution, and for wastewater treatment. And so this is really referred to as the energy and water nexus. So any technology that we develop on the energy side should not increase our water footprint, and anything that we do on the water side should not have a significant energy impact. And so this is where we can really think about what can materials do for us. And so my lab focuses on two different areas. So on the water side, we look at how can we harness solar energy. So that's an abundant form of energy, but it's not in a form that we could readily use. So how can we harness that solar energy for water treatment? How can we get to zero liquid discharge, where you're extracting all the water and you don't have this brine that you have to dispose? In that process, you could recover resources. For example, there's a lot of interest now in extracting lithium from these salt brines. So how do you use materials to do that? How can we do surface modification in order to get selective extractions? And then on the energy side, we're looking at, with the goal of trying to decarbonize our energy use, we're looking at how can we use thermal energy storage. And we're looking at a couple of different applications here. So thermal energy storage for buildings, where you would operate at a temperature of under 100 degrees Celsius. And then thermal energy storage for industry, right, where they require temperatures of 1,000 degrees Celsius, for example, for steel manufacturing, where right now it's just fossil fuels being used. So if we really want to electrify industrial applications and buildings, we have to think about adding in thermal storage. We also have some work related to energy harvesting. How do we convert low temperature heat into electricity, or how do we do local thermoregulation? How do you regulate the body temperature? And then finally, we have a relatively new project where we're looking at making building materials that are carbon negative. So a lot of natural materials like wood, which we know will sequester carbon, but is not ideal for building. So how do we make insulation as well as structural materials just based on wood? And so materials really enable us to do all of these different things. And for the first part of the presentation, I'll focus on how we're using some functional materials for producing clean water or doing desalination. And then I'll touch upon what we're doing in the energy space. So when we talk about just harnessing solar energy or sunlight for desalination, one of the most common desalination technologies is just evaporation and condensation, so a distillation type of process. And you will see a lot of these evaporation ponds. So this is in a power plant, or even for lithium mining in salt lakes, especially in South America. You have these large evaporation ponds that are just exposed to natural sunlight, and over time that water evaporates and you're left with salts, or in this case with lithium-containing salts. Now the challenge with just doing this very passive solar evaporation is that when sunlight comes in, it is absorbed by a very large volume of water. So water volumetrically absorbs sunlight because it's fairly transparent in the visible and the near infrared range. So as a result, your conversion from sunlight to vapor is pretty low. It's only about 20% conversion. So that is extremely low, and because of that, you either need very large land areas to do this kind of passive evaporation, and you also need significantly long times. So for example, for lithium mining in ponds that are about a meter deep, they have to leave those salt solutions in there for 6 months to a year in order to get all of that water to evaporate. So the question is, how can we really just enhance evaporation under natural sunlight? And again, this is where we can use materials, specifically photothermal materials. So as the name suggests, you're converting those photons into thermal energy or heat, and you're localizing the heat at the surface, because evaporation is only a surface phenomenon. So if we can localize all the heat at the surface, we'll increase the surface temperatures, and that'll increase our evaporation rates. So what does a typical photothermal converter look like? It comprises a solar absorber. So this is just a material with a very high solar absorptivity. And then we need some kind of insulating foam-like layer to separate that solar absorber from the bulk liquid, because we want to keep the heat at the surface. And then finally, you have a hydrophilic wick, which is just the material that's now going to deliver water from the bottom to that surface. And so there have been several prototypes of this, mainly using like carbon-based foams. So here you're seeing a carbon foam, which is porous, and so it has a very high solar absorptivity. And because it's a foam layer, it has a low thermal conductivity. And finally, we can use a wick to deliver the water to that surface. And so what you end up getting is you can even generate steam under just natural unconcentrated sunlight, because you're keeping all the heat at the surface and not losing it to the bulk. And so you can do this even with natural materials. So here they used just regular mushrooms, which have a nice porous structure, and you can carbonize them to get the desired solar absorptivities. And ultimately, the goal is this. You want to keep all of that heat right at the surface so that the temperature increases and you can increase your evaporation rates. So again, the main design criteria for the materials is a very high solar absorptivity. Typically, you want something that's at least about 0.9, and you want a thermal conductivity that's less than 1 watt per meter Kelvin. So a lot of carbon foams can meet those criteria. Now, if you have a two-dimensional structure, the amount of evaporation that you can get is going to be limited, because the sunlight coming in is fixed at 1,000 watts per meter square, and so your evaporation rate is limited to about 1.6 kilograms of water per square meter per hour. So you still need significantly large areas to do this evaporation. So here I'm showing you the absorption profile of water, and we see that around the solar wavelengths, so here in the visible range, water has a very low absorption coefficient, which means that it's not going to absorb sunlight strongly. But if we convert that sunlight into mid-infrared wavelengths, you can see the absorption coefficient increases significantly, and all of that sunlight can be absorbed within a few microns of the water, so really just the surface. So what we do is we convert this visible and near-infrared sunlight into mid-infrared in order to increase the absorption, and now we can rely on just using thermal radiation. So there's no contact between this top layer and the solution we're trying to heat. So we don't need a porous absorber, a wick, or any insulation material. You just have to have a selective solar absorber and an infrared emitter, and then you're using thermal radiation to transfer that energy to the water surface, and it'll absorb strongly within a few microns. And so you get this surface heating effect, but with a completely non-contact type of system. So the materials we need to use for that is a selective solar absorber. And so this is a multi-layered material, which again has an alpha or solar absorptivity of about 0.95, and it has a very low thermal emissivity. And so all the sunlight that's coming in is converted into heat by this material. And it is deposited on an aluminum substrate, and we're using a metal so that it can rapidly transfer the heat, so high thermal conductivity. And on the back side, we can use this black body emitter, or you could even design selective emitters to emit exactly at the wavelengths where water shows a strong absorption. And so this allows you, again, to do surface heating And you do not have to worry about any salts precipitating because the entire process is just non-contact. So we're just using thermal radiation to transfer the energy. And so experimentally what that looks like is if you have this beaker of water and you have your selective absorber and emitter taking in sunlight, the top surface of your water will increase in temperature. Here it increases from around 22 to a little bit over 40 degrees Celsius, while the bottom water, so down here, just remains at that ambient temperature. So you're only heating the surface. And so if you let this process run for a couple of hours, you can evaporate all the liquid, and then you're left with just the salts that crystallize. And so you can completely remove all the water. And here's just some modeling we did to again show that the heat is really just localized at that surface, and the bottom of the water remains at ambient temperature. So we can look at a conversion efficiency for this full process. So how much of the solar energy that's coming in is being used to evaporate the water. And we can break down that efficiency into three subparts. So the first one is the efficiency of our absorber. So this is the material that's really taking in the sunlight and converting that into heat. And so here we have a fairly high efficiency because of the optical properties of the selective solar absorber. Next, that heat has to be transferred from the infrared emitter to the water. And so in this case, because we're just using radiative heat transfer, we need very high view factors. And so you see there's some losses there in the system. And then finally, the heat that reaches the water surface, what percentage of that is used for evaporation versus other thermal losses. And so that's where you see we take a bigger hit. But overall, we can get to conversion efficiencies from sunlight to evaporated water of about 70% compared to what I showed you initially for these evaporation ponds where it's only around 20%. And so you can still do a very passive process, but by using the right materials and leveraging the inherent absorption properties of water, we can significantly increase that thermal efficiency. So we've also looked at, instead of this two-dimensional structure, what if we work with 3D structures? So for example, adding these micro patterns on a 2D surface, or creating a cone, a cuboid, a block, or a cylinder. So in these cases, you can significantly increase your evaporation area because you have all this three-dimensional surface, but your ground area does not change. So you get a much higher projected area, which we call this evaporation area index. And then we looked at what geometry would give us the best performance under sunlight. And so if you have, solar noon is a 0-degree angle, so the sun is vertically above, or at a 45-degree angle. And we looked at which geometry allows you to maintain the highest temperatures for evaporation throughout. And what we see is we can get the highest evaporative fluxes at both the 0 and the 45-degree angles if we use a cylindrical structure among these different ones that we looked at. And then we can also look at the capillary lifting limit to see how far up the water can be drawn by the natural porous structure, and that'll allow us to define exactly what height we want these 3D, what diameter to height or aspect ratios we want these three-dimensional structures to have. And so we went with a cylindrical structure. And here now, again, the material becomes important because we have to be able to absorb the solar radiation. And so we use graphene oxide, which we can functionalize we just take a cotton rod and functionalize it with graphene oxide. And we can get the desired properties. So this is just some SEM images. And you can see the outer surface of the cotton rod is all covered in the graphene oxide. But if we cut it at the middle, you can see the inside is still very much just the cotton. And so that's where the capillary wicking is happening. And then that water is evaporated from the outer surfaces, which are coated black with graphene oxide. So it has a very high solar absorption. So that's what I'm showing you here. The light absorption for this 3D graphene oxide is the green line. So almost 100% light absorption. So a very, very good solar absorption across the entire solar spectrum. And at the same time, we can maintain a low thermal conductivity. And so here again, showing the thermal conductivity remains pretty similar to the cotton itself. So the graphene oxide does not impact the thermal conductivity significantly. And so we're able to stay under that 0.15 watts per meter Kelvin, so still fairly insulating. And so we're not losing that heat. So this is a collaboration with UC Berkeley, and we're looking at how can we functionalize this graphene oxide further to do additional things such as selectively recovering lithium from a lithium-sodium brine. And so these are some experiments that we've been running recently, looking at if you have a small amount of lithium in a predominantly sodium solution, can we get spatial separation of the lithium from the sodium as well as across the radius? And so we're seeing that because of solubility differences, we're able to concentrate the lithium while most of the sodium precipitates out like this. And so this is one project where we're looking at trying to further optimize the lithium selectivity and extraction using just this passive solar evaporation system. So moving on, we're also looking at how do we really handle these situations when you have a lot of salts that precipitate out. Over time, you're basically blocking all of those pores, and you're also losing your solar absorption because you're now covered with these white salts, right? And so we're looking at how can we modify or tune the salt precipitation on different surfaces. And so specifically what we've seen in the literature is, you can create these types of regular microstructures on your substrate in order to create hydrophobic or superhydrophobic surfaces. And then if you add hierarchical roughness, so now you're adding like nanoscale as well as microscale roughness, then you could get not just superhydrophobic behavior, which means that your water really does not wet the surface, but you also get the water to roll off the surface very rapidly, so it doesn't adhere to the surface. And then if we look at salts, there was this paper last year which showed that as your water droplet evaporates and your salts are left behind, if that is happening on a textured surface and under a temperature gradient, your salts can form these legs. So your salt crystals essentially form these legs and eject themselves from these textured surfaces. And so looking at this, we said, okay, how can we modify our surfaces to get the water to roll off so that it's not staying there and evaporating to cause precipitation? And even if there is precipitation, can we get these salts to form the legs and lift off the surface? And so really we can do this control of the surface morphology as well as the surface chemistry to get the kind of wettability and adhesion behavior that we want. And we're doing this by creating superhydrophobic surfaces. A lot of work has been done on this topic in the past, but the biggest challenge has been that the surfaces are not durable. So after you use them, especially in a salt environment, you see that those surfaces over time lose their superhydrophobic behavior. And so we've been using a lot of tools in the IEN, and I have a seed grant from the IEN that's helped us look at low power plasma etching. So here's the contact angle on a polymer substrate without any surface modification. And then if we do this plasma etching process, so we use a reactive ion etching process in an oxygen environment, and we're able to modify the contact angle to get it to the super hydrophobic state. And if we do additional measurements on this, you can see that the droplet will actually roll off the surface as soon as we start tilting it. So it shows that it's also a very low adhesion surface, which is very important. The other technique that we're employing, because we're working with these polymers, is that we're using micro hot embossing. And so with this, we can essentially create like a mold, and then you transfer the pattern from the mold to your polymer surface. And so we can create these cone or pillar-like structures, and we can adjust the distance between those pillar structures. We can adjust the height of the pillar structures, or we could make these pyramids, cubes, all sorts of different patterns, and we can really play around with the spacing and the height in order to give us this desired behavior, which is we want the water to roll off and we want the salt to lift off. And so we're doing some preliminary experiments with the micro-embossed surfaces, and we see that they're very stable under the salt environments and temperatures that we work at, and we're currently characterizing exactly how to optimize these surfaces in order to get us very repeatable super hydrophobic behavior. So that would allow us to really control the movement of water and salt on different surfaces as we do desalination. So most of what I talked about so far has been focused on these evaporative phase transitions, so looking at evaporating the water. But there are other thermal separations that do not require that liquid vapor phase change, right? And the main reason to look for alternatives is that it's a very, very energy intensive process because of the high latent heat of vaporization that water has. And so we've been looking at alternate techniques. So one is a hybrid membrane and thermal desalination system. So in this you have your salt solution or your feed on one side of a semi-permeable membrane. And on the other side, we have a draw solution. And this draw solution is essentially made out of a material that has a higher concentration than the feed. And so the water is naturally going to flow across the membrane till you have chemical equilibrium. And so once it draws the water till these two sides attain equilibrium, then we're left with this diluted draw solution. So we don't have our clean water yet. So then we have a thermal separation step where the diluted draw is heated, but it does not have to be heated to temperatures close to boiling. We just have to heat to a critical temperature, which allows the water to separate from the draw, and then you can reuse the draw and you have your fresh water. And so the materials that enable us to do this are thermally responsive ionic liquids. Specifically, these are ionic liquids that exhibit a lower critical solution temperature behavior, or LCST. So what that means is at room temperature, the ionic liquid and water across all concentrations form a single phase mixture. But as we start heating up, we hit this two-phase boundary, and then at a certain critical temperature, our ionic liquid and water are now immiscible. And so because of density differences, the ionic liquid settles at the bottom while the water layer floats on top. So this is also a thermal separation, but it's purely a liquid-liquid phase transition rather than the liquid-vapor phase transitions we were talking about. And the biggest advantage in this case is that you can have much lower enthalpies for these phase separations compared to the latent heat of vaporization. And so looking at the mixing enthalpy, these ionic liquid water mixtures exhibit a negative entropy of mixing, and that's what really causes them to show this LCST phase behavior. So if we're able to hit the critical temperature, which as you can see here only needs to be a few degrees above ambient, the higher up you go, the better your separation, but typically around 60 to 70 degrees Celsius is that target upper temperature. And so here, looking at how do you get this LCST behavior. So really it's a combination of the material, the ionic liquid cation, and the anion has to have this balance, very subtle balance in its hydrophobic and hydrophilic characteristics. Because if it's too hydrophilic, you get a very miscible solution. It'll never phase separate. If it's too hydrophobic, it'll always be two phases. And so there is this sweet spot, this region in between, that allows us to increase temperature and create the two phases. So some of the ionic liquids we work with, again, just organic salts, right? It's a phosphonium dimethyl benzene sulfonate and a trifluoroacetate. There's a few different ones that have been reported in the literature to have this LCST behavior. And the properties we care about are the water activity or the osmotic strength of these mixtures, which varies as a function of concentration. And so depending on what kind of water you're trying to treat, you could vary the concentration of your ionic liquid. And then, of course, the phase diagram itself is really important to characterize. And so we just use cloud point measurements with a UV-Vis spectrometer to generate these phase diagrams. So this is what that thermally driven phase separation looks like. So this is the ionic liquid and water mixed at room temperature. And you can see it's a single phase mixture. As we start heating it, it forms these almost like a milky solution. And so that's what we call the cloud point temperature. And then finally, after the entire solution is heated up to that critical temperature, we get the two layers to separate. And there is a discernible phase boundary, and the water-rich phase floats on top of the ionic liquid-rich phase. And so temperature enables us to go from this single phase mixture to the two phases. And so what we think is happening in the process is, so the ionic liquid is dispersed within the water phase. As we increase temperature, the ionic liquid starts clustering. So that's what we're showing here. You form these clusters. And then finally, when you hit that critical temperature, you have created a sufficient number of clusters that allows you to now just form that second phase. And we've seen some evidence of this. So looking under a high-speed camera, we can see the phase boundary, and then we see these droplets of the ionic liquid phase, which are kind of trapped within the water-rich phase, and then we have the same down here. And so ultimately, these droplets or these ionic liquid clusters coalesce and form the second phase. And so we're trying to understand the kinetics of this process and how can we use different external forces in order to speed up that phase transition. So that's all the stuff we're doing on the water side. And I'll just briefly share some of the things we're doing related to energy as well, and the role that materials play in this. So as I mentioned, we're looking at thermal energy storage. And so the question is, so why thermal energy storage? So if we look at the residential building sector, this is the energy use by different end users. And you see that space heating as well as water heating make up about 60% of the energy use in buildings. So those are just thermal loads. And so if we can store energy as heat and then use that energy for these thermal end uses, you could decarbonize the building instead of using natural gas or oil to provide the heating. So there's a number of ways in which you can do thermal energy storage. There's just sensible heating. So in this case, just the temperature change as well as the specific heat of the material you use. So just storing heat in hot water. Or we could do phase change thermal storage. So now you're storing energy in or using that latent heat. So for example, just melting ice. But there's also paraffin waxes that can be used for phase change energy storage. What we're focused on is thermochemical reactions, where now energy is stored in the heat of reaction itself. And so one example is these salt hydrates. So these are salts with a certain number of moles of water attached to them, and they can reversibly release the water and reabsorb the water in the crystal structure itself. And the reason why we're interested in that energy storage is just because of the amount of energy that we could store and the volume required for that storage. So for a building application, because space is really important, so we want a compact solution, and you can see that we need only about 2 cubic meters of the thermochemical material to store the same amount of energy as these other energy storage cases. So how does it work? So we have our salt hydrate, and if we apply heat, we start dehydrating the material. So that is an endothermic reaction, supplying energy, and we're charging our thermal battery in that process, and we release water molecules. So you get a dehydrated version of the salt. And then when we want to release that energy, we just run the reverse reaction where we introduce water molecules, so in the form of relative humidity, and that creates an exothermic chemical reaction where the salt is hydrating again, and that process allows you to discharge the heat that is stored. And we would discharge this heat for a building application. And so we're looking at designing a packed bed reactor with these thermochemical salt hydrates in order to charge and discharge energy as heat. So this is thermal energy storage at temperatures under 100 degrees Celsius for buildings. Some of the challenges we have to be wary of are that when we dehydrate the salt, as the salt is releasing its water, it can pulverize, which means that it is just going to crack into these much smaller particles, and that's because of these thermal stresses as the salt is releasing and absorbing the water into its crystal lattice. When we could also see other challenges such as agglomeration. So rather than individual salt particles, if your relative humidity is too high or if your temperature is too high, you melt the salt hydrate and you get this agglomerated material, which is no longer going to allow you to transport water vapor effectively. And so these are some of the major challenges, and that has resulted in the energy density, or the reaction enthalpy, over a few cycles. So it starts up over here, but as we cycle the material, even just 20 times, that energy density drops to 60%. And so that is because of these instabilities or irreversibilities in the chemical reaction itself. And as a result, your reaction is also going to become a lot slower. So the kinetics are going to be slower because you have all of these non-ideal states. So one of the things we're looking at is trying to stabilize the salt hydrates And so we're making organic and organic composite. So here's the salt, the inorganic material, and then we encapsulate the salt within a hydrogel network, which is still highly porous. And so these are SEM images of some of the initial syntheses we've done. So this is now the encapsulated salt, and the structure is still porous to allow you to do your heat and mass transport, but the salt is held in place so that it cannot just leak out or pulverize because it's held in place. So we've seen some improved performance in terms of cycling using these matrices. And the particle size also has an effect. So working with the larger particles versus ball milling it to get these, smaller particles that are about 10 microns in diameter, we can see when we do TGA that the ball mill salt dehydrates quicker and hydrates much quicker than the pristine salt. And as a result of that, the energy densities from the ball mill salts tend to be a lot higher than the pristine salt. And then I'll very quickly talk about some work that we're doing in collaboration with Boston University, looking at very high temperature thermal energy storage. So this is for temperatures close to 1,000 degrees Celsius. This is mainly to decarbonize industrial processes like steel making, cement manufacturing, where they require these high temperatures. So when we talk about 1,000 degrees Celsius, there's really only a few materials that we have as options. And so they're either ceramics or it's graphite. Those are pretty much the only materials. These are all the different material properties that matter for high temperature thermal storage. And on the spider chart, if we plot what graphite looks like, it does pretty well in most categories, but not so much in terms of its mechanical properties. And then if we look at ceramics, it does pretty well for most properties, except it's not electrically conducting, and its thermal conductivity is also a little bit lower. And we want a high electrical conductivity to charge the material with electricity, so just by joule heating. And we want a decently high thermal conductivity so that you can extract the heat easily. And so we've been working with composites, so combining the benefits of ceramics and graphite in order to get these desired properties. So this is ceramic powder, so this is just aluminum oxide with graphite, and then we sinter it at about 1,700 degrees Celsius, and this is what the sintered pellet looks like. So you can see that we've really densified the grain structure to create these rigid sintered composites. And so the idea is to use this for high temperature thermal storage over 1,000 degrees Celsius, and we're looking at a few different ceramics to give us all of these different properties that we need. The presence of graphite allows you to make these ceramics electrically and thermally conducting, and so that's the idea behind using composite materials. So I'll just leave this slide up there for some of the other things that we're doing related to energy. So thermoelectric energy harvesting, like wearable and flexible electronics, primarily functional textiles. And then we're also looking at developing thermal insulation and building materials just based on wood and natural fibers so that they could sequester carbon. So with that, I just want to talk about the fact that previous systems are these large-scale static systems, but with materials we could really try to get to very different types of systems. And so I just want to acknowledge my research group, some collaborators at Lawrence Berkeley National Lab, as well as funding support. And thank you all for your time.
Thank you. I think we have time for maybe one or two quick questions, if anybody's got.
So you hinted at this in one of the slides. We talked about the polymer structure with a capillary bringing the liquid through with the salts. I mean, the salt works usually have like part per thousand or higher salt concentration. You see that precipitation of salt coming through.
Right.
Do you notice blocking as those salts just crystallize so much that it destroys the capillary function over
Yes,
time?
absolutely. So we see if you operate these, structures for more than a few hours, you start seeing the evaporation rate dropping, and then we can look at cross sections of the material and we just see salt precipitated in the pore. So a lot of times the way it's addressed in literature, they run it as a batch process. So as soon as they see a lot of precipitation, they will just flow clean water through it to dissolve the salts, and then they will repeat the process.
Oh, and also another question on the thermal evaporation. So for the 3D structures, you saw that the efficiency of evaporation was like higher, but I guess I was a little confused because wouldn't the, radiant flux of the sunlight still be the same? So would there be any limitations on like the energy versus the surface area? I guess I wasn't
So
sure
it's really, that's a good question. So it's really just playing with the area. When you have a 3D structure, you have all of this surface area on the sides, but you're normalizing to the area of to the projected area, right, which is the ground area. So, but you actually have a lot more area on the surface. That's the first thing. The second thing is with the 3D structures, we also see that it's able to harness ambient energy. And so your energy input is no longer just the sunlight, you also get a big benefit from ambient energy.
So I have a question about the application. You talk about to deploy it. How are you going to deploy it from this small structure in the natural outside door, the lake?
Yeah, so for evaporation ponds, the way we envision it to work is essentially like a series of these structures. So not just one large structure, but you would have a series of structures in specific locations on the evaporation pond. So currently we're talking to a company that does lithium extraction in the Atacama Desert in Chile. They struggle a lot with evaporation during the winter months because of the lower solar input. And so we're looking at how can we take what we've done at the lab scale and try to do a field test to see how the system would perform at larger scales.
All right, let's thank our speaker one more time, and we'll see you in a couple of weeks.
Thank you.